We are now recording.
Great.
Hey, Jim.
All right. Well, first of all, yeah, welcome everyone. Thanks so much for coming. Thanks so much to Tom for inviting me. Very happy to be here. I would normally be in my office, but Endicott is currently hosting the NCAA Division III Hockey Championship. And so they've asked us all to be remote for today. So I'm broadcasting from home, and I hope that works okay. But it does mean I'm presenting from an iPad rather than my usual computer, so it might be a little bit new for me. So I'm going to try to share my screen here. Hopefully this works. All right, now hopefully can people see the first slide there?
We see your desk. Oh, there's the first slide. Logic from scratch.
Perfect. All right, good. So that's up. And yeah, my computer doesn't seem to want to do the normal slide presentation, so I'm just working from a PDF, but hopefully that won't be too distracting. So to begin, let me just give you three pictures. On the left, this is from the Cueva de las Manos in Argentina, an ancient set of cave paintings, kind of stencils of hands from maybe 6,000 or 7,000 BC, something like that. In the middle, we have markings of cuneiform from ancient Mesopotamia, maybe 3,000 or 4,000 years later. And then on the right, some sort of traditional tally marks from a prison, I think somewhere in upstate New York. In each case, I'd like to suggest that we have a kind of primal insignium. That there's a sense in which the minimal written sign is a mere indexical mark of difference. The kind of minimal written sign would just be some kind of mark. Something has been marked here. Well, what is the difference a difference from? It has to be some more or less homogeneous background or substrate, some kind of sheet or clay or material in which the mark is made and is retained. But such a mark is not just an index. There's also at least a minimal iconicity, what Peirce would call iconicity, which is having some kind of qualitative form. And in the case of a mark, this is the basis of its iterability. That if you look at the example of the cuneiform, we can see the same shape appear in different orientations and so forth. Or in the tally marks, we see the same kind of mark appear again and again. And this iterability allows a mark to take on a symbolic role, a kind of conventional role with respect to some kind of system of meaning or a representational structure, so that we can decide upon the rule that one tally mark represents one day in prison. Once we've created that convention, we can then use these marks to keep track of how long we've been there. So I want to begin with an observation and a question. The observation is that a scratch mark of whatever type seems to have some kind of optimal signifying simplicity, right? At least with respect to human perceptual apparatus and our ability to leave or make a mark, making a kind of single scratch seems like a kind of optimal or natural way, not in the sense of nature versus culture, but natural in a kind of mathematical sense, the way that a certain notation or a certain type of function might be natural. My question is there a similarly optimal or natural syntax for logic, in particular for classical logic? And is there a sense in which Peirce's system of existential graphs is this optimal syntax, or at least approaches it, approximates it? So the talk is organized like this. I want to focus on this system of existential graphs, talk about some of its very general features, and then look in some detail at the alpha level, which corresponds to classical propositional logic, look at the structure more or less as given by Peirce, and then to turn to the formalization of Peirce's system in category theory that I've worked on with my colleagues, and then try to do the same thing for beta, although the categorical formalization there can be really no more than just a quick indication. But basically, I want to talk about alpha and then beta, which corresponds to first order logic with identity, and then conclude by trying to think about Peirce's existential graphs as a whole in light of his philosophical concerns with semiotics and what he calls cynicism, his sort of philosophy of continuity. So to begin with a acknowledgement that this is work that I've been carrying on now for 12 or 13 years, I think, with a couple of colleagues, my friend and colleague Gianluca, also at Endicott in the mathematics department, and then our colleague Fernando Tomé down at the Universidad Nacional del Sur in Argentina. He's an economist, but also a mathematician. And the three of us have worked together on this stuff now for quite some time. And this really is the work that I'm presenting. I definitely want to, credit them equally, at least with the, with the insights, whatever insights we've gained, I think, into the system. So Peirce's graphs can be thought of as a kind of unified diagrammatic framework for a kind of hierarchy of logics. The alpha level corresponds to classical propositional logic, beta to first order quantificational logic with identity, and then the gamma level, which I won't even begin to address today or talk about at all, corresponds to modal logic and various ways of trying to think about higher order logic. And Peirce never really completed the gamma level. It didn't, I don't think you could say that it's finished in the way that alpha and beta were at least largely complete. The essential unifying principle I would like to claim about the system of EG is that logical operations for this diagrammatic syntax are write, erase, and copy operations on subgraphs. And I think this is what makes the EG quite special. Logical operations are operations on subgraphs, and a subgraph is a topologically coherent area on what Peirce calls the sheet of assertion. So to clarify, the sheet of assertion is Peirce's term for the place where these graphs are scribed or written. It's just a blank sheet is the easiest way to think of it, like the sheet on the left. And if you look on the right, what do we do on the sheet of assertion? We scribe assertions. So these might be sentences. Peirce wrote far more than he published, which is true. Or we might assert something like A in the context of doing logic. We're just assert a term representing any assertion whatsoever, right? Or we distinguish it from an assertion B. But what we write on the sheet corresponds to something that we assert. And to talk about a topologically coherent area on the sheet of assertion is just to note that whatever it is that we scribe, to the extent that we scribe it according to some sort of rule, we want to be able to erase or copy or write that component without kind of cutting it in some arbitrary way. We don't want to split an assertion in the middle. We don't want to divide up, copy part of the A, but not the other half. So I've just indicated here with dotted lines, a topologically coherent area would be something like a selection of the written sentence, or a selection of the area around A, or the area around B, or the area around both A and B, which we might erase or copy, for example. So with that as just a very generic picture, what is this system? It's an attempt to represent logic through these topological operations on subgraphs. We start with the alpha level, and the syntactic elements of alpha are essentially closed curves in the plane. And these typically are ovals or circles, but they could in principle be rectangles or other shapes, but it's convenient to draw them as ovals. Sometimes Peirce calls them seps. I prefer calling them cuts. And just notice that if we don't allow the cuts to intersect with one another, then once we've written one cut on the sheet of assertion, if we want to write another cut, we basically have a decision to make, right? And it's a simple decision. Either we write our second cut outside our first cut, or we write it inside. And there's nothing else we can do, right? Those are our only two options. It might be big, it might be small, but basically, if we're thinking topologically, a cut distinguishes an inside from an outside, and that means that we have various ways of nesting cuts at various depths because we don't allow them to intersect. And then Peirce introduces the convention that we think of levels of nesting in terms of even and odd parity. So as I've indicated here, the even areas are the sheet of assertion itself. And then if we count down 1, 2, going across 2 cuts, we're in an even area again. Whereas if we cross 1 cut, we're on an odd area. And if we cross 3, again, we're odd. So we'll have systems of nested cuts, and then these divide up the sheet into even and odd areas. And then the only other syntactic element we need are something like characters to represent assertions. And so we have here a kind of informal recursive definition that would produce all the well-formed alpha graphs. We call these graphs, the sheet of assertion is itself a graph. Any character or variable is a graph. If we have any two graphs, alpha and beta, then we can juxtapose them on the sheet. And notice that we can move them in any orientation. So A, B, and BA are in no way distinguished topologically, but that putting them on the same sheet together forms a graph. And then if alpha is any graph, we draw a cut around it, and that too is a graph. So think of that then applied recursively, and we get the class of well-formed alpha graphs. And then we have a system of deduction rules, and these are the operations on subgraphs that will preserve logical validity. So if we have a graph that represents an assertion that is true, we can perform any of these operations, and we will also have at the in the aftermath of that operation, the result of that operation will also be true. So we can inscribe or scribe any graph on any odd area. We can erase any graph or subgraph from an even area. Given a subgraph, which again is a kind of topologically coherent piece of the sheet of assertion, which basically means we can't cross a cut and we can't take just part of an assertion. We have to, if we take part of a cut, we have to take everything that's inside. Once we've chosen such a subgraph, we can copy it onto the same area where it appears, or any area that is nested on the area where it appears. We just can't copy it onto any part of itself. It sounds a little bit complicated to explain, but in practice, it's a very straightforward way of pick any subgraph. You can iterate it down into further nestings, but you can't iterate it up across the cuts. And if there's a subgraph that can be iterated or could have been produced by being iterated in this way, we can de-iterate it. So we can erase a graph if it could have been iterated from some other subgraph. And then finally, if we have two nested cuts with nothing in between them, You can think of this as a kind of double negation, and we could either write them around any subgraph or erase them from around any subgraph. So a picture is worth 1,000 words. These are just informal, kind of intuitive pictures, but I think it's a much clearer way, especially if you haven't encountered the graphs before, to see how these things work. We can write odds. So if we have the graph at the top on the left, this would represent if a cut negates the conjunction of its contents. So we read from the outside in, and this says it is not the case that R and not P. In other words, R implies P. But you can see that R appears on an odd area, P appears on an even area. We can add a new subgraph, Q, to that odd area. So now we have R and Q imply P, or it is not the case that R and Q and not P. Similarly, we can erase even, given the graph, it is not the case that R and not P and Q, we can simply erase the Q because it appears on an even area. And it's important to remember that Q here doesn't have to just be a variable, it could be an arbitrary subgraph. It could have a lot of internal structure as long as that structure appears entirely in that place on that area. So we can write odd, erase even, we can iterate. So if you start from the left and go from left to right, you can see that the Q is copied both onto the odd area and onto the even area. And both of these are legitimate because this is an iteration, copying down onto an area that appears on the area where Q is. I noticed that these rules can overlap in the sense that we could have written the Q on the odd area anyway because of the right odd. So we have two different legitimations for writing Q. In this case, we can think of it as an iteration or as simply right odd. But notice that this, unlike right odd and erase even, is a two-way rule. We can also pass from the right to the left. Given the graph on the right, because we could have iterated Q onto those inside cuts, we can erase them, but think of them as copying them out onto the Q on the outside. That's the de-iteration of those subgraphs. And then the final rule, the double cut, again corresponds to double negation. From the graph P and Q, we can draw two cuts around it, and we can say it is not the case that it is not the case that P and Q. And similarly, on any area, if we have a cut and then nothing and then another cut, so there's nothing between the two cuts, and then we have a subgraph of whatever constitution, we can erase the double cut. So these are the four rules, right? Two of them are reversible, two of them are sort of unilateral. And these rules, somewhat surprisingly, are sound and complete for classical propositional logic. You can do all of propositional logic with just these operations on the subgraphs. Let me give you an example. If we start from the lower left, this would be the graph P and not Q, or you can think of this as P and P implies Q, setting us up for a kind of modus ponens. We can de-iterate the P. So we're moving up now to the upper left. Now we have P and not Q. Then we erase P, which we are allowed to do because of the rule erase even. We now have not Q, and we have a double cut around Q. We can erase the double cut, and we get to Q. So this is the way that the rules are applied so as to get to derive Q from the original graph P and P implies Q. There is a lot to be learned, sort of facts on the ground as you actually work with the graphs, right? And so even if this seems a little bit if you haven't encountered these before, you might have a lot of questions. Just know that the key point here is that using simply cuts or ovals and variables, right? And these deductive rules, we get everything that we need from classical propositional logic, sound and complete system. But what I've worked on with my colleagues, Gianluca and Fernando, is to try to formalize this system mathematically so that we don't have to think about circles, but we can actually contract these things at a more kind of abstract and maybe more rigorous level. And this is where we turn to category theory. Just because of time, to try to give an introduction to this kind of mathematics would probably take the whole time that we have. But let me just give you a quick intuition in this case. This is all we need for this particular application. I will define a category here for you and call it N. And it's a category that you're probably already familiar with. It's just the natural numbers. How do we represent it? Well, we have objects and morphisms. A morphism is just an arrow between two objects. Our objects are the natural numbers, 1, 2, 3, 4, 5, and we just have an arrow going from one object M to another object N if and only if M is less than or equal to N. So you might notice I don't have arrows going from 1 to 1 and 2 to 2, or from 1 to 3, 1 to 4. And that's just to keep things clean, right? These are the only arrows we sort of need to see, but we know that if 1 is less than 2 and 2 is less than 3, sure enough, 1 will also be less than 3, right? And the identity arrows saying that 1 is equal to itself, we can kind of forget about. So hopefully that's just an intuitive picture. Basically, we have the natural numbers and an order on them represented by morphisms. This does, in fact, define what's called a category. And then we have a kind of nice, straightforward way to talk about functors from this category into the category of sets, right? And in fact, these are called contravariant functors. So you notice the arrows are going in the other way. All you need to do to understand this construction is now notice that instead of 1, 2, and 3, we have S sub 1, S sub 2, S sub 3, and these are just arbitrary sets. So we've assigned to each of our natural numbers a set. And the arrows now going from right to left are functions, arbitrary functions. So we have a function that goes from whatever set we call here S5 into the set S4. We have a function from S2 into S1. And we just mandate that these functions compose, right? Any way that we assign sets and functions to our natural numbers in this way is going to give us what's called a functor. We can collect all of those functors, and they have a nice natural way to think about mappings from one to the next, which is called a natural transformation. This entire structure is a category. It's composed of objects and morphisms. It's the category set to the n op. I apologize for the typo. The p is supposed to be up next to the n. But this has a more intuitive name. This is the category of forests. What is a forest? Most of you are probably familiar with trees. A tree is just a mathematical structure that has a unique node called the root. And then beneath that root, there are a number of other nodes that are connected to it. Those nodes may or may not have nodes below them. And a forest is just a collection of trees. So a very simple, straightforward, very useful mathematical structure. This is just one example here on the left, very simple forest. And if you think about it for a moment, it turns out that forests are isomorphic in structure to collections of nested circles. So you can create any collection of nested circles on the plane, and you will have defined a unique forest. As long as you think of these forests as not having any particular order, there's no left or right orientation. You can kind of permute them as you will. And this is at the heart of our construction, is to recognize that this easily defined object in mathematics, right? It's the functor category of functors from this category of natural numbers into set, and all the natural transformations between them actually gives us the kind of skeletons of all of Peirce's alpha graphs, right? All of these nested cuts. And it turns out that we don't even need, at the end of the day, to worry about variables, right? And the reason, and this is I think what goes deep to the to what is so interesting in Peirce's system, we can think at the level of semantics as taking the two truth values in propositional logic, right? Top and bottom, or true and false, and we can identify them with two graphs. The empty sheet of assertion, so the what is there, the blank before true in brackets, that's actually meant to be a graph. It's the blank sheet. The blank sheet we can take to be our value true, and the empty cut, just a single cut with nothing in it, we can take to be bottom or false. So we actually have two graphs that we can think of as semantic values. And that, if we sort of make that trick, then we can think of variables, propositions, as simply being placeholders for those two possible subgraphs. So this slide is meant to give you a sense of, if given the graph with variables on the left, P implies Q, we can think of all the different ways we can replace P and Q with either the empty sheet or the empty cut, right? And in fact, we have exactly 4 possibilities, and those are represented by the 4 graphs on the right-hand side. Either both P and Q are true, which gives us the upper left. P is false and Q is true, which gives us the lower left. P is true and Q is false, which gives us the upper right. And both P and Q are false, which gives us the lower right. And then, interestingly, every cuts-only graph, so every one of these forests or graphs without variables, evaluates semantically in terms of value to either the empty sheet or the empty cut, and in a way that isn't conceptually the same, because we need, in some level, we need to distinguish semantics from syntax, but they're so close that they almost become identified for Peirce's system. We can evaluate any cuts-only graph semantically in a unique way to either the empty sheet or the empty cut, and any cuts-only graph can be transformed through the deduction rules, purely syntactically, into exactly the same graph, the same valuation. And in fact, to do so, we only need 2 of Peirce's rules. And the 2 that we need are the 2 that are reversible, de-iteration and the double cut rule. And these can be repictured here for cuts only. De-iteration and iteration says on any area, if we have 2 empty cuts, we can replace them by 1, or if we have 1, we can replace it by 2, but we're in general, we want to make things smaller, right? And anywhere we have a double cut, we can erase it. And these 2 rules are actually effectively the same as those given by George Spencer Brown in his calculus of indications, which in a certain sense, through this technique of turning variables into cuts or not, we essentially identify Peirce's system with Spencer Brown's, although the way they interpreted things semantically was slightly different. But in a nutshell, we have one simple and straightforward system, which is a way of thinking about systems of forests or systems of nested cuts. Now, if that wasn't complicated enough, we can go up a level, e.g. beta, which corresponds to first order logic. So we have this framework of cuts, and variables, although we can dispense with the variables. Essentially, we have nested cuts, and this gives us all the power of propositional logic, right? So now we want quantifiers, right? And we want relation symbols, functions. Well, it turns out all we need are two new syntactic elements. We keep our cuts, we keep the sheet of assertion, but now we add what Peirce somewhat idiosyncratically calls a spot. It's a kind of strange term for it. He calls it a spot. A spot is what we would intuitively think of as an n-ary relation. So syntactically, we have some kind of character, usually a word, in this case, something like praises. And then we have a number of hooks, which we can think of as being like syntactic placeholders that determine the arity of that relation. And so we have to be a little bit careful about how we order these things, right? And there are a number of different tricks and techniques, usually we just think of these things as proceeding from the left and going in a kind of clockwise way. So what does this spot represent? Something praises someone praises someone to someone. Although it doesn't represent that claim or that assertion, it is just the possible placeholder for this triadic relation of praise, right? The hooks are not quantifiers, but they're places where a quantifier could designate some individual. The only other syntactic element we add is Peirce's notion, the line of identity, which I think is maybe the most important syntactic component of the entire system. So it's worth a kind of long quote here from Peirce talking about the line of identity. He thinks of this as first of all being just a dot. And a dot can represent kind of a something or a someone. As it's an index, right? Something is pictured by this thing. But then imagine that dot moving, and as it moves, as Peirce's kind of poetic way of describing it, it carries along its singleness and also leaves it behind in its wake. What will this result in? Whereas the single dot was but a name, a mere something, the line actually becomes a graph, right? It takes on logical consistency, not just, it's no longer merely an index, a designation of something. It now asserts something. Why? Because it has two endpoints. And it asserts that the individual designated by one extremity is the same as the individual designated by the other extremity. And in fact, Peirce develops this so that a line of identity isn't really a line, but it should be thought of as being susceptible to branching at every point along its extension. This is Peirce's notion of Terre identity, which means if you take the graph, the line of identity on the left, we identify the two endpoints, but we can add a branch somewhere in the middle, and anything attached to that new endpoint. Now we have a line with three ends, right? Or three termini, right? And we identify all three, right? So these are three endpoints of one and the same individual. So let me just give you a couple examples. These are actually from Peirce's own manuscripts, which is why the typeface is a little strange looking. So on the left, we have graphs that represent something has red pulp and something is an orange. And then on the right, you can see that the two lines have been identified, right? And so now we say there is something that is both orange and has red pulp. So this is how we interpret these. If we have an n-ary relation, then we would fill it in with that many lines of identity. So this graph tells us that something is between two things, right? And here we would have to keep track of the order, even if the betweenness has some kind of commutativity, right? In general, we would keep track of, A is between B and C, is different from A is between C and B, unless we introduce additional axioms and so forth. But the point is, we can certainly sustain relations with that are higher than arity 2, although arity 2 usually is simple for examples. So this notion of the line of identity then interacts with the cut, so that the graphs, as we read from left to right, we have something is both good and ugly. Drawing a cut around that graph negates the interior, so it is not the case that something is both good and ugly. In other words, there is no thing that is both good and ugly. The third graph tells us that something is good, and that same something is not ugly. So the negation of the cut cuts away the predication is ugly, but we have the same individual. The endpoints are identified with the two predicates. So we say there is something that is good, but is not ugly. And then if we introduce a cut around that graph, right, we're negating the claim that there is something that is good and is not ugly. And if you think about it, that is logically equivalent to saying all good things are ugly. There is no thing that exists that is good and is not ugly, right? And so universal quantification simply is this line of identity appearing for the first time on an odd area. So it's a very kind of efficient system, and it gives us the expressive power of first order logic. Just a couple more examples maybe to see how it works. To kind of clarify, we always read from the outside in. So starting in the upper left, we are negating the claim that something or someone is a Catholic, and that same someone does not adore someone who is a woman, right? So we would read this as all Catholics adore someone who is a woman, right? Which is a different claim from what we see on the upper right, which is there is some woman who is adored by all Catholics, right? And so this is how, if you're familiar with the linear notation of logic, for all X, there exists Y is a different logical statement than there exists Y for all, such that for all X, right? In Peirce's system, that difference is encoded by where do the quantifiers start? What is the first area where they appear, right? And then the graph on the bottom tells us that there are two somebodies, a Catholic and a woman, such that that Catholic does not adore that woman. So there is some woman and some Catholic such that the Catholic does not adore her. Fascinatingly, the deduction rules for this system, which is now robust enough to sustain first order logic, they are the same as the deduction rules for E.g. alpha. So we have exactly the same set of rules. All we need to do is make specifications for what we mean by treating graphs that include lines of identity as subgraphs. So I've simply recopied the 4 rules, right, odd, erase, even, iterate, deiterate, and double cut. But to give you a sense of what problems or questions emerge when we add the line of identity, well, we always need to think about this new possibility of a cut that sort of goes through a line, or if you think from the other way, the line that seems to cross a cut. To give you a sense of how Peirce's use of ordinary language to try to formulate these rules can be quite tricky at times. He says things like, a point upon a SEP is to be considered, on the one hand, as a hook of the enclosure of the SEP considered as a graph, and as such as a portion of a line of identity immediately outside the SEP. But on the other hand, any line of identity inside the SEP can only be extended to join a point or be disjoint from it, according to the rules governing a line so enclosed. Peirce is always very, very exact, but sometimes it takes a lot of work to figure out exactly what he means. But these rules can be formulated precisely. What it amounts to is Peirce wants to be very careful about what happens actually on the cut itself. That we can, in a very rough sense, we can extend a line of identity across a cut if we're going from an area to a cut inscribed on that area. But we have to be very careful. We can't technically cross the cut. We can just go up to the cut, right? And then if the rules allow us to do so from inside the cut, we can extend a line of identity to join it. So they're just very kind of subtle issues about what exactly we mean by linking a line of identity to another line if it's across a cut. But that question, right? How do we talk rigorously about these very subtle topological questions? When exactly are we allowed to extend a line of identity or not? When does it meet the cut or not? It seems like it's an interesting question. How could we, or might we, formalize this using category theory, using that same kind of technique that I showed you with alpha? And it does seem to be the answer is yes. I can only say seems at this point because we haven't yet published this work, but it does seem to hold. What we need to do is enrich that category. So if you see up here at the top, A1, A2, ... that is our old friend, the natural numbers. So we retain that same structure, which corresponds to the nestings of cuts, but now we need to enrich that base category with a lot more structure. Basically, these L sub n's and these R sub n's with a superscript, they are going to encode the relation spots and the lines of identity. And rather than try to go through the details here, just to say that what I think this approach using functor categories helps us to see is that even though Peirce's graphs are written on paper and we can modify them in these various ways, at the end of the day, we're looking at certain possibilities which are topological. And so all we don't care about how long a line of identity is, how many curves it has. All we care about is it attached to a given relation spot or not, which is just a binary question. Does it cross a given cut or not? And so that's basically, in a nutshell, what this categorical formulation allows us to do, because what we'd be looking at are functors into sets over this category. Essentially what it does is it encodes using sets, using kind of discrete elements, these decisions that we make when we specify a graph as to whether two things are joined or not, whether they're on the same area or not, and kind of where they're placed. So then finally, I'll try to wrap this up here in about 5 minutes. So we're almost done. Just to conclude, I'd like to think about these two layers of Peirce's system: alpha corresponding to propositional logic, beta corresponding to first order logic, and to think of them in the broader context of Peirce's logic, or Peirce's philosophy of signs, his semiotics, and his notion of synechicism, his philosophy of continuity. So Peirce's triadic semiotics thinks of all signs as a triadic relation, such that some object determines a representiment, a sign, in such a way that that representiment determines another sign called the interpretant, so that that relation that the representiment has to the object becomes a relation that that object has to the interpretant. It's a kind of translation, right, or communication of one relation to another. And one thing that I think is often overlooked in studies of Peirce's signs is that the representament is not the only representament in the system, but the interpretant is also a representament. And that's why I chose this. Of all, Peirce says the same thing over and over again, different formulations, different ways of talking about this triadic relation. But here I like that he says a relation of the representament to its object, which consists in it determining a thing the interpretant representation to be in the same relation to that object, which really means that in the very definition of the sign, we have an indefinite sequence of interpretants, right? It's because every interpretant is a representation, and a representation is what it is in relation to another interpretant. In principle, if we have one representation, we have some indefinite sequence of interpretants. And I think this is a clue to seeing the way in which Peirce's triadic semiotics is deeply integrated with his notion of continuity. That if we have a sign at all, in the sense of thirdness, we inevitably have a kind of continuity of interpretants that will continue, right, or extend that sign. And I think in the interest of time, I'll maybe skip a couple of these final slides. It's just that to point out that Peirce's notion of signs is grounded in his notion of the categories of firstness, secondness, and thirdness. Quality, reaction, and sign or representation. So in other words, anything that is a sign is an instance of thirdness, which is itself a sort of outgrowth of these more primordial categories, firstness and secondness. And this is what allows Peirce to categorize signs in terms of each of the three components of the triadic relation, the representative, the object, and the interpretant, insofar as that term is considered in its firstness, its secondness, or its thirdness. So if we think of just the representative, we have qualisign, sinsign, legisign, a representative understood in its firstness, understood in its secondness, or its pure reaction or being there, and then as a legisign or as its iterability. These are this is the basis for Peirce's tenfold kind of classification of signs, which you may have seen, just ways that these can be combined. But I just want to focus on the relation to the object, right? This is probably Peirce's best known trichotomy. He often talks about signs in terms of icon, which is the relation to the object being one of similarity of structure, index, which means that the object causally determines through a kind of reaction the being of the sign, and then symbol, in which the object has some kind of conventional or law-like relation to the representative. And the only point I would want to make here is that the system of existential graphs incorporates all three types of sign in a particularly integrated way. That there are various ways in which the syntax of the diagrams is iconic of certain logical relations. Probably the simplest example is the way that the commutivity of conjunction, the fact that A and B is equivalent to B and A, is pictured, right, or represented iconically by the fact that we don't care about anything other than the topological areas in which variables appear. So we don't even have to introduce an axiom that A and B is the same as B and A, because the syntax is already commutative. AB on the sheet of assertion is the same as BA, because topologically we can manipulate these things and they're topologically equivalent. And so this isn't the only example, but I think it's the maybe easiest example to see where we have a syntactical representation that itself carries with it the structure of the intended logical object. The indexical elements are based on the fact that in order to claim that something exists, you must actually physically or in some way inscribe, right? The act of inscription is an indexical relation. The actual inscription on the sheet of assertion is an existential production of the assertion itself. And then, of course, the various conventions whereby we can manipulate the graphs have the symbolic dimension. So to return to our question kind of from the beginning, is this way of incorporating iconic, indexical, and symbolic dimensions of the syntax in some sense optimal, right? Is this way of being iconic, indexical, and symbolic in the syntax somehow most natural to the kind of logic that Peirce is trying to represent? And I think that if the answer is yes, it's because of Peirce's cynicism, right? And this continues the earlier quote where Peirce is defining his three categories, talking about thirdness, which is the category of representation or semiotics. Peirce says, a mere complication of this third category, thirdness, it's essentially the same thing, was anything that such by virtue of its relations to any multitude whatsoever. And these are Peirce's sort of somewhat idiosyncratic way of talking about finite, what we would normally call denumerable, and then following Cantor, having cardinality greater than the natural numbers, or for any even super multitude, something like a class, that this category suffices of itself to give the conception of true continuity. In other words, that something about thirdness goes even beyond the discrete elements that define sets and gives us something like continuity in person. Right? In other words, at least according to my reading here, semiotics as a study of thirdness is the study of continuity. And I think that the way that we would understand that is precisely in terms of the way that in the triadic sign, the representamen determines an interpretant, which is itself a representamen for a further interpretant, and so on. So the continuity of the sign is the way that the interpretant is defined as itself a sign. And in the system of existential graphs, we have constitutive components that are understood in terms of their continuity, in particular the sheet of assertion, the cut, which is a kind of break in continuity, but one that is perfect, right, in the sense that it is unambiguous which continuity it cuts, right? It is a closed curve as opposed to, say, a line, which will interrupt continuity, but only in a local way, right? A closed curve is that unique form in the plane that produces a discontinuity between two areas. And then the line of identity is a continuity that, interestingly enough, in some sense can cross these cuts, right? Or can be continuous across discontinuity. To bring it all together, quote from Peirce, of the many things he says about logic, this is one of my favorites. It says, logic for me is the study of the essential conditions to which signs must conform in order to function as such. In other words, it's something like a transcendental semiotics. It is the conditions of possibility for genuine sign functioning. That logic is the transcendental study of signs. Well, if logic is transcendental semiotics, and if semiotics itself is the study of continuity, I think we have at the very least two kind of well-motivated questions. One, might this actually help to explain why mathematical domains like topology and homotopy type theory turn out to be so useful in representing logic, right? Might this be a way to think about why these particular mathematical domains work so well in doing what we want in terms of logic? And to wrap things up, might this suggest that a kind of simple topologically structured syntax would be what is wanted from an optimal or natural system of logic representation? So thanks a lot. I would love to hear any questions, comments. I've got just a short list here of papers that I've published with Gianluca and Fernando that are basically, if you're interested in more of the technical details, you could go to those. And for sure, most of them you could probably find online somewhere or other. If you can't find them, certainly just email me and I'd be happy to send you those. So yeah, thanks again. And I'll turn things back to the gallery here.
Yeah, I guess just raise your hand if you got a question.
Yeah, it looks like Siddharth. Or Siddharth.
You had it up there. Yeah.
I was clapping, but I can think of a
Oh,
question.
sorry, I thought that was a question.
No worries. But sure, I'll ask a question. So you said that there something, I think, towards both the beginning and end of Peirce's system being optimal in some sense. Like, do you have any sense of what the technical underpinnings of such a result might look like?
That's a really great question. That's, for me, it's very much an open question in terms of a rigorous answer to that. To what would an objective measure of optimality in diagrammatic representation mean? But it does seem right to me that category theory is the right place to look mathematically for that kind of criterion. That there's a reason that naturality was at the very emergence of category theory as an autonomous mathematical domain. It was
Sure.
It was in order to treat what are called natural transfer, what came to be called natural transformations that category theory developed. Category theory is somehow uniquely situated to work inside highly structured environments so as to find the best or the most optimal adjunction or addition or subtraction that maintains as much structure as possible, preserves as much structure as possible.
Sure.
Right? Yeah, go ahead.
So do you think like your construction might be like universal in some technical sense or something like this?
That it would be nice if it was as simple as that. I think there's probably what one would have to do is find something like or define the category of diagrammatic systems of logic, right?
Mhm.
And then you would look for a terminal object or maybe an initial object, right? But it doesn't seem like there's an easy way to get all at once all the possible ways that we could diagrammatically represent logical operations. But
Okay.
but that's, I mean, for me at this point, it's nothing more than a kind of clue that Peirce's system so readily is represented by a simple and straightforward functor category.
Right.
That it some sense it would be too much to say it's the optimal system, but it has a certain optimality just in the sense that we can make a translation of it into mathematics in kind of one step. Whereas if you try to do that with just the linear notation for classical propositional logic, you just need more steps, right? You need to, even if you go all the way down to NAND, right, which is quite close in spirit to Peirce's cut, you still need to somehow build in the structure of parentheses, right? Whereas Peirce's system, that I think the most intuitive way to see what is at least an aspect of optimality is Peirce manages to use one syntactic element, the cut, to capture both parentheses and negation.
Yeah, I think people say something like there's no syntactic bureaucracy is a term I've heard.
I really like that. I hadn't heard that, but that's a really nice way to put it.
Yeah, proof theorists say something about this. Well, thank you very much.
Mm-hmm. Yeah, thanks for the question. And there might be another page of, I just know that I can't see everyone. So if you're raising your hand, it might be better to,
How
it
about
looks like your name says Sarah, but I'm not sure if that's the right name. But yeah, if you raise your, go ahead, please go ahead. Oh, please be sure to unmute yourself.
Is that all right?
Yes, now I can hear you.
I see. The name's Jim. I'm sorry. That's my wife's name.
Hi, Jim.
Anyway, uh, I thought I heard it said that non-denumerability was sufficient for continuity. I just wanted to make sure I heard that.
No, oh, no, that Peirce doesn't say that. He says that continuity is, he says thirdness is such that it will be true of relations that hold across all cardinalities. I mean, he doesn't, that's what he uses his particular terms, but that would be it's almost the opposite. Rather than there being a cardinality criterion for Peirce that would say continuity begins at this cardinality, Peirce says continuity is the kind of thing that transcends cardinality entirely. Which is, it's a very extraordinary point of view. But yeah, Peirce, I think, was he was very excited with the work of Cantor, but I think he really understood. He saw the limitations in set theory that a lot of mathematicians weren't able to see until much later in the development. He saw that at the end of the day, no matter how you pack things in, how dense things become, you just can't build continuity out of sets. And it doesn't mean that continuity isn't present, right? It's just for Peirce, it's, sets depend upon continuity, but continuity can never be built from sets. So continuity it's actually a kind of ontological condition rather than epistemological.
That was very helpful. But did you say that sets depend on continuity?
But I think from Peirce's point of view, continuity could never be constructed on the basis of discreteness. You can never add enough points together to get continuity, because continuity.
I think it's a very good point that cardinality doesn't settle continuity, but finite sets aren't continuous, are they?
For Peirce, in a funny way, they are. But that's in the sense that they wouldn't be what they are without some continuity somewhere.
Okay.
And that's again where Peirce is very strongly influenced by Kant. So he's always thinking of something like transcendental conditions, but in that and maybe this is going a bit far afield, but if Peirce's Kant is much more like Schelling, Peirce takes Kant in a Schellingian direction where the transcendental is how do I want to say this? It's the ontological process whereby time and matter come into being, rather than something like an epistemological framework for knowing objects, right? It's transcendental, but it's transcendentally constitutive of the real, not of knowledge or just experience in a Kantian sense. It looks. It looks like John Schmidt and Joe Rudman. I'm not sure who had their hand, but maybe if we take them in that order, is that okay?
Joe's had his hand up for a while. Let him go first.
Oh, maybe he should start. Yeah.
Thanks. Yeah, sort of related to what you just said. I can see an easy, or what seems to be an obvious extension to fuzzy logic, but I don't see an obvious extension to quantum logic.
Yeah. It's fascinating to think of what Peirce would have made of quantum mechanics. I mean, I think he would have felt vindicated in many respects, because he, another ism that he advocated besides his cynicism and his third ism is Tukism, right? He believes that there is something like real aleatoric character in the universe, right? And so I think he would have loved the fact that quantum mechanics seems to suggest this in some way. But I think he would have been disturbed by the discreteness, the fundamental discreteness of quantum structures. So it's hard to know kind of what to make of it. But yes, I think that there is a sense in which Peirce almost goes so far as to identify the continuum with the real, so that if something is real, it is continuous.
Oh yeah, and I think of quantum mechanics as continuous. So the discreteness is emergent in certain circumstances. The globally is continuous.
Yeah, but your point about fuzzy logic, it is interesting that, e.g., alpha and beta are thoroughly classical, but Peirce did work, put a tremendous amount of effort into the level of the gamma graphs, where he was essentially trying to deal both with modal and higher order structures at the same time, and really made some pretty interesting strides in those directions. So that would be the place to look if you're thinking about maybe multi-valued logics or fuzzy logic. There might very well be places in the writings on the gamma graphs. Yeah, there's a John Schmidt.
Yeah, hi, Rocky. Thanks for your presentation. Appreciate it. One thought I had was, that you covered the alpha and beta in a way that I think is pretty accessible for people who maybe aren't familiar with it. And it seemed like that was your goal, was to try to make it accessible as much as you can in a brief presentation like this to folks who are unfamiliar. One suggestion I might have going forward is Peirce himself finally made a switch in about 1911, where he realized that shading oddly enclosed areas was a superior, more iconic way to signal those, as opposed to cuts, for a couple of different reasons, but mostly, again, because they're more iconic. It's a different surface that those graphs are essentially being scribed on. At least conceptually, that's what's going on, as opposed to his original concept where it was a cut in the page that you flipped over and all of that. He decided that was a really bad way to go, and blamed that for why his prolegomena, the Apology of Pragmaticism, ended up being 100 different terms and so many pages and so forth. But anyway, I found also that shading those oddly enclosed areas is helpful if you're doing it, at least in electronic format. A little harder when you're drawing things by hand,
right?
But it's helpful because then you don't have to count cuts to figure out whether you're odd or even and things like that. You can just look and see if it's unshaded, it's even; if it's shaded, it's odd. And I think Peirce adopted that primarily to simplify his own presentation of existential graphs to new audiences, and it might be something for you to consider going forward.
Yeah, thanks for that. I mean, yeah, I do like that representation, although I find it to be completely compatible with the earlier recto verso way of conceiving it. If you imagine that the sheet is white on the top and black on the verso, right? Then it works in the same way. You just, a cut flips it so that now you see the black, but then if you write a cut inside, you flip that and go back to white.
Right, but when you start getting into beta and you have lines of identity and the lines that create the cuts, you got to make sure your lines of identity are nice and heavy to make sure it's the differentiate. So I think especially for beta, the shading is a clearer way, at least, of distinguishing, because it's really just the boundary between the areas that you're concerned about. It's not an actual sign that's being drawn on the page like a line of identity is.
That's interesting. Yeah, yeah, thanks for that, because I hadn't thought of that with at alpha, it does work nicely, but it's true that with beta, especially if you think of the cut going across, and then if the line of identity goes across and then you have to flip something, you're sort of twisting the line. But this is what's so fascinating about Peirce is once you start reasoning about the graphs, we inevitably slip into a kind of physical discussion as if these are physical objects, right? But in fact, they are just descriptions, right? And this is for me why the translation into category theory is very helpful, because there's a danger if we take the kind of materiality of the graphs too seriously. On the one hand, it's wonderful, and there's something really powerful about thinking of that, right? On the other hand, if we start saying things like, oh, but every cut when I draw it has some kind of thickness, what do I do with the thickness? We might end up building too much structure, right, into the formalism. Whereas what's nice about category theory is you can, it's abstract enough that you don't need, you get the power of the iconicity, but you don't risk turning your representational device into the thing itself.
Yeah, the challenge then is you think explaining existential graphs in 45 minutes is hard. Try explaining category theory to an audience that isn't familiar with it.
Exactly.
I mean, I'm familiar with it, but I'm not very conversant in it, so that would be a challenge for me. Even, I mean, even with the flipping over with the heavy line, you know, that's why Peirce would say it's not the same line. You can't cross a cut with a line of identity. It's a ligature then. That's two line of identities that are end to end at that boundary. So that's why I think he eventually went with the shading, because he didn't have to, I mean, he loved to have lots and lots of words to explain things, but it was one way to maybe cut down on the cognitive load of his explanations of the system.
Yeah. And it is interesting to think, even just as a practical question, is there a way to get the advantage of the shading without having to do this a bunch? Because again, like if you teach it and you draw it on a board, if you have to do this,
yeah,
it looks ugly for one thing. But if there would be a neat way, I wonder, is there some way to mark the shading on a computer? The nice thing is you might just be able to hit a button.
Right. That's what I said. Yeah. By hand, it's a much more challenging thing. The only other comment I'd like to make was you did make kind of an offhand remark about thirdness being an outgrowth of firstness and secondness. And I think Peirce would put it the other way, you know, that we prescind firstness and secondness from thirdness. You can't build up to thirdness from firstness and second. I just wanted to clarify that for the audience. And that ties into the subsequent comment during the discussion already about, you know, as a finite set, continuous. Well, I think Peirce's conception was that anything that's finite or discrete sort of precipitates out of the underlying continuum that is more fundamental. The whole is real. The parts are, to a certain extent, enchirationis that we artificially create for whatever purpose as we go through our analysis. And you know, I have the position that goes for signs as well. You talked about signs as a paradigmatic example of continuity. Well, if you consider the whole universe as a semiotic continuum, and any individual signs with their objects and interpretants are things that we prescind for some analytical purpose, I think you get a very interesting approach then to not only semiotics, but then metaphysics as the application of that at the next step up in the architectonic. But I'll leave it at that and let others have their opportunity. Thanks very much again.
Yeah, thanks so much. There is Jerry Chandler. Oh, you're muted.
Thank you very much for your presentation. It was quite clear in the direction you were taking, and I would appreciate I will appreciate the opportunity to read your papers and look more carefully, particularly at the strong reliance on the incorporation of category theory, which is a rather recent development in mathematics, and with respect to Peirce's works. I was particularly somewhat surprised that you used the natural numbers, 1, 2, 3, 4, etc., as a foundation of the difference between categories, and that this enumeration. And it seems, and then the diagram you showed also put an order relationship on the categories. And I don't quite understand how this relates either to the, if you would, the topology, general notion of topologies, and which generally don't rely upon a numbering system in this sense, or how it stands to creating relationships between categories. In the diagram you gave, I saw several levels, and the arrows were arranged in order from the prime category of the natural numbers to other levels. And so anything you could offer to me to help me understand how this is working in your mind would be very much appreciated.
Sure, and maybe, I mean, it's important to disambiguate when, you know, Peirce uses the language of categories to talk about his firstness, secondness, and thirdness, right? Drawing on Kant and before him Aristotle. So he wants to kind of reinvent the category of categories as a threefold kind of quality, reaction, representation, or sign. And that's not, category theory has nothing to do with categories in that sense, except that Eilenberg and MacLean, I think if they, whoever ended up choosing the name, some sort of borrowed the term from Aristotle, right? But it's there a priori, there's no connection between Peirce's categories and the categories of category theory. It's just the same word. And the use of the category of the natural numbers to encode the alpha graphs is just a function of the discreteness of the cuts, in the sense that once we have a cut in the plane, right? A plane is complicated, right? And if we think of paths in the plane, all kinds of complicated things, but once we have a cut, we have carved the sheet into exactly two pieces, and that two-ness is totally discrete.
Yeah. Thank you very much. You completely answered my question.
Oh, wonderful. Yeah. Thank you.
Hi, I guess I'm next. So,
Hi.
hi, Rocky. This was great. Thank you very much. I hope you will forgive me if I ask a question that may only be tangentially related.
No, those are my favorite kind.
Yeah, well, good. Well, so here goes. Do you have any idea or any thoughts or any knowledge about how Peirce's diagrammatic notation compares with Frege's in logic? So the creation story that we're all told, those of us who teach symbolic logic, is that in the beginning there was Frege and Russell, and they shook hands, and then Russell proceeded to write the notation that we use for propositional first order predicate logic. But I've heard it said that Frege's notation, because it is, I don't know, different, and here I'm pleading naivete, it nevertheless represents structure diagrammatically in a way that Russell's and therefore ours today doesn't. So do you have thoughts on that? Does it relate to?
Yeah, it's a great question, and there seems to be there's work on Frege that emphasizes the kind of the compositionality of his diagrammatic representation, which is what it amounts to. Is that you know, again, what I find special about Peirce is the fact that we're ultimately talking about operations on subgraphs, and that's what in some of the research that Gianluca and Fernando and I have been pursuing recently, we've been turning to combinators, which is I think there are a lot of similarities between combinators and Peirce's logic, in the sense that you think about a term might have a whole bunch of structure, but you manipulate it as one thing, right? And this ability to parse out structure and trees are always the natural way to represent these things, right? That you have a node and you might have a whole bunch of stuff below it, but that node gives you a thing that you can manipulate, copy, erase, and by erasing that one node or copying that node, you copy everything that comes below it, right? And to Frege's original diagrammatic notation can be read that way, which brings it much closer in spirit to Peirce. Although I think that there's nothing in Frege that corresponds to the line of identity, right? That Frege just designates individuals with variables, which are names, you know, and ultimately that puts us back in the same world where we have to keep track of variables, we have to worry about variable substitution, and you know, and maybe this is a bit of a stretch, but I think there's some sense in which Peirce's notation stands to Frege's, even interpreted in the best possible light, somewhat as combinators stand to the lambda calculus. You know, lambda calculus is great, but you still have to deal with all these rewriting rules. You have to be sure that the variables don't cross each other, right? So it's elegant, but it's not as iconic as just being able to partition out these operations as such, right? And so that's the, you know, Peirce with the line of identity gives us a quantifier that is the thing itself, right? It just is a designation of a something such that it's capable of being attached to many different things and yet remaining the same thing. Yeah, there's a wonderful logician. Maybe someone on screen knows. I'm just blanking on her name right now, but she's a logician at professor at Haverford College. At least she was at. Yes.
Yes, in fact, I have had conversations with her, and that's what prompted this question.
Yes,
because
her work on Frege I love it. It's wonderful because, at least from my point of view, it shows that we can understand Frege in a more diagrammatic way that is really much closer in spirit to Peirce.
So she has a somewhat historical philosophical thesis there that we've lost something, or that those of us who study logic, like, gosh darn it, that was a path not taken that we should have taken, because something is missed by this deflationary in a stylistic sense, and also, I guess, a metaphysical sense of system that we get from Russell. So that something could have been different, a better understanding of logic. So do you have the same kind of thesis with Peirce, that not only is it maybe more natural, but that logic, I don't know, would have turned out differently, or it should have gone, we should have not, Peirce's work shouldn't have been lost, something like that?
Yeah, certainly. You know, and the alternate history genre is always both, you know, a lot of fun, but also kind of dangerous to take seriously. But you can also turn it around from a critical point of view, right? The alternate history genre is critical genealogy, right?
Mm-hmm.
It's not just a matter of saying how could have things been different, but given that things were the way they were, what decisions were made that we take for granted today that actually foreclose certain kinds of thinking or certain kinds of
yes
practice.
That's a great way of putting it, right? That's what I was wondering, and it's interesting to think about.
Yeah, I mean, I think with my kind of gut feeling with Peirce is that the power of this more topological representation is that logical and metaphysical questions are much more closely aligned, right? Like, I mean, I love sort of, you know, there are traditions say in esoteric Islam that the Aleph is the primordial act of creation, right? Allah creates creation by a stroke, right? The Aleph as a stroke, right? And this is, you know, again, quite close in spirit maybe to someone like Schelling, for this kind of primordial act of division whereby God kind of alienates God, or gives up God's self, right? Or maybe in Jewish mysticism, this kind of withdrawal of the divine. Right? These are, you know, grand metaphysical conceptions that are ways to try to make sense of being, right? And typically those would be thought of as completely beyond the pale of anything like logic, right? But maybe a notation like Peirce's suggests that the primordial beginning is something like a mark, right? And maybe, you know, maybe there's more to things that a lot of philosophers who want to dismiss as just goofy occult metaphysics, right? Well, maybe it's occult metaphysics, but maybe it can be clarified, and maybe it's good metaphysics, and maybe it's actually logical metaphysics, right?
Yeah, or conversely, and maybe a bit more modestly, philosophers think that logic can be metaphysically neutral or brings no
Yeah.
epistemological baggage with it. Everything brings some kind of baggage with it.
Right. Yes, absolutely.
Yeah, well, good. Thank you. No, that's very, very interesting. Thank you.
Yeah, thanks for your question.
I would just make a passing comment here in that, yes, there is the possibility that somehow a wrong turn was made in the history of logic, and we ended up with a modern version of set theory as being the foundations. The other possibility is, of course, that there are, in fact, two different forms of rationality, of reasoning, one being based on simple numbers or discrete numbers, and the other form of rationality being based on continuity. And these are just functionally and foundationally different from one another in the forms of logic that they generate. It is an alternative hypothesis.
Mm-hmm. Although, I think a lot of philosophers don't rest content with any kind of pacifist dualism. I love a passive, like, oh, there are two different ways, they're just different, and we're all happy. Like, temperamentally, I'm great with that. But I think a lot of philosophers always then want to ask the question, well, but then, the synthesis or the division of the two, which side does it fall down on? And this is one of those things where I do think that there's a fundamental duality between the continuous and the discrete. But I think it's very difficult not to ask which one somehow is primordial. And maybe it's the wrong question to ask, but I do think a lot of philosophers do want to ask that. I think Peirce did. I think Peirce wanted to. Peirce would have liked, I think, your comment, but I think he also would have wanted to say yes, but that alternate mode of reasoning of the discrete depends upon and is grounded in the continuous. I don't know if he's right about that, but I think that my sense is that would have been his claim.
Well, consider the fact that the beta graphs themselves could be an example of that relationship.
That's true, and I really like your. I would tend to side with your point of view, in that that's one of the things that I think is aesthetically so invigorating in the beta graphs, is the way that they somehow manage to be both continuous and discrete. Though somehow the interaction between cuts and lines of identity is almost a kind of logical music. And I think that it's better to leave it at that rather than to try to reduce one to the other. To see that interaction actually in play is part of what's enjoyable about working with that system.
It turns out, of course, that each chemical element has its own identity as a number. And yet, if you want to do the dynamics of chemistry or the dynamics of quantum mechanics, you must use continuity. And of course, all the disassociation of any chemical element gives you electrical particles, which you then treat in motion as continuous functions as you describe their action. And so I don't see that's any big natural gap between the notion of discreteness and continuity. It's a question of what you're trying to represent.
Yeah, and that's a very interesting point, in that Peirce he took inspiration for his beta graphs from chemistry, right, and from notations of chemical bonds. So that I think is a really useful way to think about the kind of underlying dynamics of the beta graphs, is to think about diagrams of chemical bond structures, and to say that maybe chemical bonds are really logic-like in the way that they, support these material objects all around us, right? We're not surrounded by atoms, we're surrounded by molecules, right? And these molecular structures are the condition of possibility of more elaborate forms. I think Peirce is closer to chemistry than to physics in that regard,
Or closer to music.
or maybe to music. Yeah.
Or biology,
Mhm.
there aren't discrete species.
Right.
Right,
That's
like
and
that.
especially the example of populations
Hmm.
as something that's kind of beyond the difference between the individual and the continuous, or the individual and the general.
Well, I feel like I should introduce some level of discontinuity here. I always thought there should be a name for that kind of joke that people make at philosophy papers, where you try to wrap the content of the talk into the what you're saying, but I've never been able to think of it. Anyway, so if we were just sitting in a physical place, we could just wander off as we want. I guess we can do that anyway, but I want to say you're off the hook, Rocky, if you want to be off the hook.
Sure. I mean, I love talking about this stuff, but I do think, people, it's the post 5 o'clock, so it might be time
Right.
for a glass of Merlot or
Right.
a whiskey.
Right. Well, thanks for doing it. Thanks everybody for coming.
Thanks so much for the invitation. It's so great to be here for the Logic and Reasoning Institute. I'm so glad that you have the opportunity to make these kinds of things happen. And
yeah, well, more to come. And some of you I know, and I will see you around.
great.
Thanks, Rocky.
Yeah, thanks everybody.
Thanks very much.
Yep. Yeah, so we'll be in touch. But thanks. That was super fun.
Great. Yeah, I enjoyed it. Hope it went over well. It seemed like a good group. Yeah,
I thought it was good. I thought it was great. And I'll try to figure out what's up with the recording and do something with that.
Awesome.
Okay. See you
Well,
around.
yeah, we'll be in touch. Yeah, good to see you.
Bye bye.
Yeah, thanks a lot. Take care.
Yep.